Okay, good morning statics class. We are back to method of joints. Again, this is ENGR 214 ampersand. This is Bellingham Technical College, winter 2020. And this is our second example of the method of joints for truss analysis. Just to recap, in the method of joints, we start by, if we can, solving for all the support reactions by treating the truss as one big rigid body, FBD the whole truss, apply reactions appropriate for each support, and be sure to include all of the applied external forces. Don't miss one. This will give you the support reactions, of course, as well as all of your externals, which you should already know. Then, step 2, you go through and you put each joint in static equilibrium. You assume that if a truss is pushing on a joint, the joint is pushing back, it's in compression. Vice versa would put the member in tension. And we simply sum up the forces in the X and the Y and the Z for each joint. Obviously, if we're in 2D, it's just the sum of the forces in the X and the Y. So each joint will give us two equations of equilibrium and as many unknowns as we have members for which the forces are not known, which typically would be the number of members going through that joint. Okay, so for our second example, we have this partially cantilevered truss. Again, it's simply supported because we have a two-force hinge here at point D, and then we have a simple roller support which can only apply loads in the vertical of point A. So we start with a whole truss FBD, and to make sure I don't get ahead of myself and start looking into the truss when I don't want to, I use my trick of kind of drawing a blob that encompasses the whole body and is rigid and transmits forces, so I can FBD the entire thing. I include a force in the X and a force in the Y at D to represent the hinge support, and a force only in the vertical at A to represent that roller support. My blob FBD, so to speak, has to include critical dimensions between all of the forces. So we have the 6 feet replicated from here, from point A to point D, horizontally on the supports. I have the 4 foot offset to point C, where we have the 300-pound applied load. Now, normally, if I had anything of interest being applied in the horizontal, I would have taken over my 3-foot dimension to my whole truss FBD. But as it turns out, because this 300-pound applied load is only being applied in the vertical, and I'm going to be taking my moments here about point D, I have my radius from the applied force, or from the point to the applied force, R cross F. So I don't actually need the 3-foot horizontal distance between D and C. Okay, having taken over my forces, known and unknown, and my critical dimensions, I can now apply all 3 of the equations of equilibrium to my whole truss FBD. And sum of the forces in the X is trivial because there's no forces in the X. Sum of the forces in the Y gives us A sub Y plus A sub D plus 300 pounds equaling 0. So we know one of these has to be going the other way. And the sum of the moments about point D will give me A, since A has to be opposing the 300 pounds to keep the body from rotating about point D. And that gives us a value for A, which is 200 pounds. That has to be in the upward direction to keep moments balanced to about point D, and so that means D sub Y has to be negative 500 pounds. So we got our support reactions, got our external loads. So now we're going to go back to our truss and we're going to start walking through it, putting each joint pin in static equilibrium. So we're going to start with A, where we have support reactions. So at joint A, we have a 200-pound support that we just solved for, applied upward in the vertical direction, and I'm choosing to represent both member AB, the force from member AB, and AD both being in tension. I'm using some geometry to get a value here for theta, and that's based on the 6-foot horizontal and 3-foot vertical. Take the arc tangent of 1/2, and I get about 26.6 for theta, and so I'll use that to get the x and y components of AB. And we have that over here. Our sum of the forces in the x is force AB times cosine of theta plus all of force AD, and then in the y we have our 200 pounds upward plus AB sine theta. So solve for those, and I find that AD is as I assumed it was, in tension. So I have 400 pounds tensile force in member AD, and not surprisingly, member AB turns out to be in compression because it's the only thing balancing my upward 200-pound force, and so I denote that with a C. So I now have the forces that are being carried by member AD here, 400 pounds of tension. Yep, tension. And then in AB, I've got almost 450 pounds of compression. So we're going to move on to pin B. So we can represent now, we have a number for force, the force from member AB coming up towards pin D, and an angle. This is, I can use my geometry of vertical angles and say that if the angle between member AB with the horizontal is theta, it's still theta with the horizontal, with this horizontal angle. I have a vertical member BD that I've chosen to represent as being in tension. We'll see if it is. Probably is, because it has to oppose this. And then I've got BC, which I've chosen to be in compression, which I know it's going to have to be to oppose, again, my force AB. So, sum of the forces in the x, I have cosine theta times 447.2 pounds in positive, x direction being opposed by the entire force BC going in the negative x direction. That gives me BC as being 400 pounds compression. I plug that into my sum of the forces in the y, and I have 447.2 sine theta minus all of force BD, because it's all in the vertical, and that gives me force BD as being 200 pounds tension. So my assumed directions for these two were correct. So looking back up here, this is in compression at 400 pounds, and this is 200 pounds tension. So that only leaves, we have two more joints that we could look at. We only need the force in member DC, so we're definitely going to have a check equation. So if I take pin C as my next point, I pick up the 300 pounds applied external load. I have 400 pounds being applied in the positive x direction coming from my force from BC, which is in compression. So if the pins are, again, applying compressive force to the member pushes back on the pin. So that gives me insight into direction. And then I have the force due to member DC coming out at an angle phi, which I have to go back to my schematic to get. So I have 4 feet in this direction and 3 feet. So the way I've drawn the angle phi, it should be arctan of 4/3, which should give me 53 degrees. So again, sum of the forces in the x. We have DC sine of 53 in the negative x direction plus 400 pounds equals 0. So that gives me DC as being 400 pounds in positive, which means it's in the assumed direction, which means it's in tension. So that's actually the highest force that we've seen so far for a member. So it's definitely carrying the highest load. I can do a partial check by plugging in the y component of DC and making sure it equals 300, which it does. So I got one check there. And then I can use my final pin down at the support D as a complete check of all of my assumptions to date, including the support reactions. So I can put all of the loads and all of the members that I've solved for so far that are going through pin D along with their respective angles, and then the downward support reaction, and make sure that they all tally up to 0 in the X and the Y, and they do. So I know that my truss has been solved correctly. So this is the last of our method of joints examples. Basically, they're all the same. You do them all the same way, even if you're doing a space truss. You just add one more dimension. You will only have moment equations, part of your equations of equilibrium in the overall truss FBD, the whole truss FBD, where you're solving for your support reactions. Once you go into the joints themselves and you start looking at the pins, or if you have a space truss, probably a ball and socket representation, you're not going to be able to carry any moment in those joints, definition of a truss. So all you'll have are some of the forces in the X and the Y, or X, Y, and Z. Solve them and generally work your way from one support to another, picking up the already solved force members at the subsequent joint to make your solutions, to make your math easier. And remember that if you have a solvable truss, you'll have the same number of equations as unknowns. And even if you can't pick up if you can't solve, if you have too many members coming into a particular pin, generally you'll be able to solve for that excess number of unknowns in the next pin over. So that is it for method of joints. Our next topic will be shortcuts and tricks, and then ways to look at whether or not a truss is solvable, in that is there a single unique load for every member? Is the truss overspecified? Is it underspecified or unstable and maybe accelerating? We don't have enough constraint, and how we can find that by just simply counting the number of members and pins. So we'll see you next for that.